Now, one thing that they stress to us is that when you see the cosine of u plus v, that's not cosine times u plus v. You can't like distribute that cosine to the u and to the v. That's not the same thing. What we're saying here is like the cosine of 30 plus 45. So that would be the cosine of 75. Whereas over here, it's the cosine of 30 plus the cosine of 75. I'm sorry, cosine of 30 plus cosine of 45, and that would give me two entirely different things. So to illustrate that for us, that's exactly what we see in example number 1. They have us do the cosine of 75 by writing it as cosine of 30 plus 45, and then they have us do cosine 30 plus cosine 45. Again, stressing this idea that those two are not equal to each other. All right, why are we even doing this? Why do I want to do this? Well, we've memorized values from the unit circle. So, like, we know the cosine of 30 and we know the cosine of 45. Wouldn't it be nice if I could get another value without having to memorize anything new? And so that's what we want to see here, is that I can find out what cosine 75 is without having to memorize anything else, because I can use the values that I already have memorized. If I rewrite cosine 75 as the cosine of 30 plus 45, that's cosine 75, right? Then I can use that addition formula from up here. Cosine u plus v is equal to cosine u cosine v minus sine u sine v. And what I'm going to do is I'm going to put 30 in the place of every u, and I'm going to put 45 in the place of every v. So let's come over and do that. Let's put 30 in for u, 30 in for u, and then 45 in for v, 45 in for v. Now, these are filled in on your note sheets, which is abnormal for us. The notes are all filled in there for you, just because this gets really detailed, and it's a lot of writing, and it's hard to follow all the values and the simplifications. And so I wanted to give that to you to make it a little bit easier for you. All right, so if we start with cosine 30, all right, we know the value cosine 30 is square root of 3 over 2. And cosine 45 we know is square root of 2 over 2. Then minus some more values that we know. We know sine 30 is 1/2, and sine 45 is square root of 2 over 2. All right, so let's simplify. Order of operations says that I've got to multiply and multiply before I subtract. So let's go through and multiply. Square root of 3 times square root of 2 would be square root of 6, and 2 times 2 is 4. Over here, 1 times square root of 2 would be square root of 2, and 2 times 2 is 4. And now that I have a common denominator, I can subtract, and that's going to be my final answer. So it gave me a way that I could find the cosine of 75 without having to memorize any more values. Now, again, going back to that idea that it's not going to give you the same answer as if you distributed that cosine and made it cosine of 30 plus cosine of 45. Of course, cosine 30 is square root of 3 over 2, and cosine of 45 is square root of 2 over 2. When I add those, you can see those answers aren't anywhere close to the same thing. Now, these little red numbers that you see circled here are going to be the homework problems that correspond to the example that we're doing, so that'll kind of give you a guide to go by. All right, so 9 through 18, they asked me to do the same thing that we just did up here, only this time I'm working in radians. So I've got the sine of pi over 12. Now, they were kind enough to me on this problem, and sometimes even on the homework problems, to tell me, figure out what the sine of pi over 12 is by rewriting pi over 12 as pi over 3 minus pi over 4. What if they didn't do that? What if they didn't just flat out give it to me and tell me how to do it? How am I going to figure that out for myself? Okay, well, we still are more comfortable in degrees than we are in radians. So what you might want to do is say, okay, pi over 12 is the same thing as 180 divided by 12. And so that would be 15 degrees. So if I switched that in radians, pi over 12 to degrees, it would be 15 degrees. So then what I want to do is think of, how can I get 15 degrees by using values that I already know? So suggestions, how do I get 15 degrees only using values that I already memorized from the unit circle? 45 minus 30. What else? Is there only one way to do it? What else would give me 15 besides 45 minus 30? What are values that we know? 60 minus 45. 135 minus 120. 150 minus 135. I mean, we could go all day long all the way around the circle, right? So any value that is a value off of the unit circle that you already know, you can add it and subtract it for different values to create different combinations. And that's exactly what's happening here when they say find the sine of pi over 12, which of course is just the same thing as the sine of 15. We could come over here and say that would be the sine of 60 minus 45, or the sine of 45 minus 30, or the sine of 135 minus 120, however you want to write it. So that's why they've chosen pi over 3 minus pi over 4. But if it was not given to you, that's how you could figure it out for yourself. Okay, so let's use, since this is sine subtraction, let's use our sine subtraction formula from the top of the page. So we're going to go through and we're going to put pi over 3 in the place of u and pi over 4 in the place of v. So pi over 3 in the place of u, pi over 4 in the place of v. And then we can simplify. So we can say, okay, these are all values that we know off of the unit circle. So sine at pi over 3 is square root of 3 over 2. Cosine at pi over 4 is square root of 2 over 2. Minus cosine at pi over 3 is 1/2, and sine is square root of 2 over 2. And then we're just doing simplification again, right? We have to multiply each of these before we subtract. And we end up with the exact same computation that we had in example 1. Are we always going to get the same answer? Well, no. In example 1, we had the cosine of 75, and in example 2, we had the sine of 15. What's unique about cosine 75 in relation to sine 15? They add up to be 90 degrees. Why is that important? What do you call things that add up to be 90 degrees? Complementary, right? And we had some kind of formula that dealt with complementary things.
Cosine 75 is equal to sine 15.
Yes, cofunctions of complementary angles are equal to each other, right? So 15 and 75 are complementary, and sine and cosine are cofunctions. So cofunctions of complementary angles are equal. So that's why these just so happened to be equal. The nice thing about that is if I happen to remember that property from, say, 100 pages ago, I wouldn't have to do any of this work right here. Because I would say, ooh, that and that are cofunctions, and they're complementary angles, so their answers are going to be equal. I already know what the answer is before I start. That'd be nice, right? All right, look at the next one. Example 3 is not in your textbook, but we did have a block of these in the homework, so I wanted you to have an example to go by. In example number 3, we're going to go backwards. They've been giving us the trig function and asking us to expand it. Now they're going to give me the expanded form and ask me to condense it back down. So that's what's going on here. We've got cosine, cosine, plus sine, sine. Cosine, cosine, plus sine, sine. So if you look at the top of the page, which of those formulas is cosine, cosine, plus sine, sine?
Cosine times u minus v.
Cosine u minus v. That's our cosine subtraction formula. So I'm going to do cosine u minus v, because that's the formula that fits what we've got here. And so you can see we're going to put 10 in the place of u, and we're going to put 15 in the place of v. So let's come over here and do that. Put 10 in the place of u and 15 in the place of v. So 10 minus 15 would give us cosine negative 5. All right, examples 5 and 6 go back to simplifying and verifying. Sometimes the directions will just say simplify. Sometimes the directions will say prove or verify. And remember, if it's a prove or a verify, you can only work on one side. But the work is still the same no matter which way we go. So for example number 5, this was actually a prove or a verify. It says prove the cofunction identity cosine pi over 2 minus x is equal to sine x. So that's an identity we were given that we're supposed to already know, but here we want to prove that it really is true. Okay, so I'm going to look at cosine pi over 2 minus x and go, hey, I need my cosine subtraction formula. So here's that formula from the top of the first page. What are we going to put in for u? Pi over 2. What are we going to put in for v? X. So let's go through and put pi over 2 in the place of u and x in the place of v. I don't know the cosine of x because I don't know what x is, but I do know the cosine of pi over 2. What's the cosine at pi over 2? Cosine at 90 degrees or pi over 2? 0. So we're going to have 0 times cosine x. Then over here, what's the sine at 90 or pi over 2? 1. So we'll have 1 times sine x. So now we've got 0 times cosine plus 1 times sine. So 0 times cosine is going to drop out and just leave me sine. So we proved or verified that that was true. If it had just been a simplified, then it wouldn't have said from the very beginning what I was looking for, and I would have worked my way to the end the same way. All right, look at the next one. For the next one, they don't give me the answer. It just says simplify. It could say verify if they told me what I was trying to get to. So for this one, you'll notice that I have tangent of two things being added, so I'm going to use the tangent addition formula. What do you want to put in the place of u? Theta. And what about in the place of v?
3 pi.
So let's go through and put theta in the place of u and 3 pi in the place of v. Now, I don't know what tangent theta is, but I can figure out what tangent 3 pi is. So I'm going to come over here and work on that kind of on a little side note over here. 3 pi is not on my unit circle that I've learned. It's too big, right? Our circle only goes up to 2 pi before we start, going around for multiple revolutions and coterminals and that kind of thing. But the standard circle that we work with, the first revolution is 0 to 2 pi, so 3 pi is too big. We said if you don't like the name, you can change it. How do we change it? Add or subtract 2 pi to find coterminals, right? So let's subtract 2 pi from this, and we'll have tangent of pi. So if I'm trying to figure out the tangent at pi, here's pi over here. Remember the ordered pair is -1, 0. Tangent is y over x. So if I put my y value 0 over my x value -1, 0 over -1 will give me 0. So everywhere I have a tangent 3 pi in this problem, I'm going to replace the whole thing with 0. I'm not going to replace 3 pi with 0. I'm going to replace tangent 3 pi, the whole thing, with what it's equal to, which is 0. So I don't know what tangent theta is, but I do know this whole thing, tangent 3 pi, just equaled 0. I don't know what tangent is, but I do know tangent 3 pi is 0. So tangent times 0 would give me 0, and so I'll just have 1 minus 0 in the bottom. So tangent over 1 would just give me tangent. So they said simplify, but they could have from the very beginning said verify that this is equal to tangent. We've actually already done cosine 75 today. That was one of the first problems on the top of the page. But on the homework, they'll give me something like this one. It said find sine, cosine, and tangent of 75 by doing 30 plus 45. Okay? So we've already dealt with cosine today. Sine would be very similar. I would go through and say the sine of 75 would be the sine of 30 plus 45. I would go through and put 30 in the place of u, 45 in the place of v. 30 in the place of u, 45 in the place of v. And then I would use those values that I have memorized off of the unit circle, use order of operations, and come up with my final answer. So sine and cosine fairly straightforward. Where we're going to have some difficulty is with tangent, and so I want to look at another one of those with you in addition to the one that we just did. Let's look at tangent 75. All right, we would rewrite that as 30 plus 45, and so again, I'm going to put 30 in the place of u, 30 in the place of u, and I'm going to put 45 in the place of each of the v's. So you won't have any trouble with your values because we know those. Tangent 30 is square root of 3 over 3, tangent 45 is 1. Tangent 30 is square root of 3 over 3, tangent 45 is 1. You're going to get right here and put a great big circle around this and say this is your answer, and then you look in the back of the book and they have this, and you're like, how in the world did they get there? All right, well, here's the problem with our answer right here. It's actually got a couple problems. I have a fraction inside of a fraction, which is a complex fraction. I'm never supposed to leave an answer that way because it can be simplified. I also have a radical in my denominator. I'm not allowed to do that. I have to rationalize. So let's start with getting rid of all the fractions before I start throwing radicals into this thing as well. All right? So to get rid of the fractions, anytime you have a fraction inside of a fraction, we always multiply by the least common denominator. So if I'm looking at this thing and, we did square root of 3 over 3 times 1 and just rewrote it as square root of 3 over 3 is the only change from here to here. But if I'm looking at this thing, I have denominators of 3 and 1. So the least common denominator then would be 3. So I'm going to multiply top and bottom by 3. As long as what I do to the numerator, I also do to the denominator. It's a legal move. I'm not changing anything. So square root of 3 over 3 times 3 would leave me with just square root of 3. Square root of, 1 times 3 would give me 3. In the denominator, 1 times 3 would give me 3. And then square root of 3 over 3 times 3, the 3's would cancel and just leave me square root of 3. So that's much better. I don't have fractions inside of fractions anymore, but I do still have radicals in the denominator. So when I have just a plain radical, like if it was just square root of 3, I could multiply top and bottom by square root of 3 to rationalize. But because it's square root of 3 in combination with something else, then I'm going to need to multiply by the conjugate. Remember, that's when you have the exact same numbers, but the opposite sign. And again, what I do to the bottom, I also have to do to the top. So I'm going to go through and FOIL each of these. So I'm going to FOIL the numerator. Square root of 3 times 3 is 3 square roots of 3. Square root of 3 times square root of 3 would be 3. 3 times 3 would be 9. 3 times the square root of 3 is 3 square roots of 3. In the bottom, I'm going to FOIL. 3 times 3 is 9. 3 times a positive square root of 3. Negative square root of 3 times 3, and then negative square root of 3 times positive square root of 3 would be negative square root of 3, negative square root of 9, which would be 3. So now we can do some simplifying. 3 square roots of 3, 3 square roots of 3 is 6 square roots of 3. 9 and 3 is 12. In the bottom, the 3 square roots of 3 and negative 3 square roots of 3 drop out. That leaves me with just 9 minus 3, which is 6. It would be tempting to cancel this 6 top and bottom, but remember you can't cancel things that are being added, only things that are being multiplied. So I have to factor that 6 out of the top, and then I can cancel it top and bottom to get to that 2 plus the square root of 3. So again, the problem for you on 9, 13, and 17 is not going to be using these new formulas. You're going to get here with no problem at all. But then you have to do some joyful, ugly algebra to get from here to here, and that's where we get tripped up a little bit. So I wanted to go through one of those in its entirety with you just to review some of that rationalizing and that kind of thing. Okay?